Alright, so the last topic we're going to talk about here with the periodic table is electronegativity. So this is a physical property of elements. And so essentially what it is just, if we have a larger electronegativity, which I always abbreviate as EN because shortcuts, right? Well, that means that there's a greater attraction between an atom and its electrons. So, think of it like a game of tug of war. So this is going to start to bridge us into the idea of multiple atoms interacting with each other. So this is the kind of last property of an individual atom, but it's one that applies to how it behaves around other atoms. And so what this is going to pertain to is the interaction between an atom and electrons. And so these can be their own electrons, these can be electrons from another atom, but what that is. And so there's an attraction. So the nucleus is positive charge, the electrons are negative charge. And so the first thing is that opposites attract. Just like you have two poles on a magnet, you have like North Pole and South Pole, and they attract to each other. Same idea here. Positive charge attracts negative charge. And just like two North Poles or two South Poles on a magnet will repel, so will positive charges and negative charges. They will repel each other as well. And so that's going to be kind of a key idea going forward, is that opposites attract like charges repel. So electrons actually repel other electrons, and the nuclei of atoms are repelled by the other nuclei because it's two positive things. But this opposite charges is what keeps the electrons centered around the nucleus of an atom. Alright, so there's going to be a couple trends I want to talk about, and then this will be incredibly important for the next section too, when we start talking about compounds. So make sure it's making sense. And so there's sort of two ways that electronegativity has a trend, and they both pertain to the periodic table. Now there's always exceptions to the rules, and so I won't do anything that breaks the trend that I tell you. And so the first one is that as we go on our periodic table, we go across a row, as we go from left to right, electronegativity is increasing. So we'll have two trends. When we go left to right, that equals an increase in electronegativity. And I'll explain why in a minute. And then the other trend, so this is a two-dimensional surface, right? So we got left, right, now we're going to have up, down. And so as we go from the bottom to the top, we also get increasing electronegativity. So as we go up a column, electronegativity increases. As we go across a row, electronegativity increases. Now, the reasons for this are different, but it's the same underlying principle. So, I talked about how opposites attract. Alright, so you got to have opposite charges to have attraction. But also, just like with magnets, I don't have any to demonstrate, but as you can hold them away from each other, and as you bring them closer and closer together, eventually they'll just click. They're going to overpower you and they're going to click. If you get them just close enough, they're going to snap together. And that's because as you get the items closer and closer together, the attraction increases. And so being far apart decreases attraction. Being close together increases attraction. So there's a distance factor. And small distance equals increased attraction. And then the other one is a little more straightforward. What if you just have stronger magnets, right? Well, you can have stronger, charges. For example, the hydrogen nucleus only has one proton. The helium nucleus has two. So it has +2 in the middle. This is a +1. Lithium's a +3. So every proton we're adding increases the charge of the nucleus. And so that's going to be a stronger positive attraction to the electrons that are around it. And so, there's also the size of the charge. Greater charges, greater attraction. Smaller charges, weaker attraction. And so we're going to see these two variables playing off each other as we go through the periodic table. Now, as we go left to right, as I've already mentioned, like if we go from hydrogen to helium, the number of protons increases. So the charge is increasing. And so those electrons are seeing a more and more positive nucleus. Or if I go from lithium to beryllium, or beryllium to boron, boron to carbon, more and more positive nucleus. If I'm an electron, I'm feeling more and more attraction to that nucleus because it's more and more positive, all the way through to neon, on the second row here anyway. So I go from lithium to neon, it's going to increase. Because remember, it's a different trend for up, down, so we'll talk about that. So right now, just left, right. So as we go left to right, we get more protons in the nucleus. That's going to equal more positive charge, and that's going to equal greater attraction. And so that's what's happening. So the left to right, I think, is pretty straightforward. If you go from lithium to carbon, you go from 3 protons to 6. So you have a nucleus that is twice as positively charged. So it's going to look twice as good to an electron. And so they're going to start to be more strongly attracted to that nucleus. They're going to have larger electronegativity. Alright, so as we go from the bottom to the top, what's going on? Well, don't forget about distance, right? So every row, as we go down, this has 1 electron shell, 2 electron shells, 3 electron shells, 4. Every one of those electron shells goes on the outside of the last one. And so the nuclei get bigger and bigger and bigger. So you start with like hydrogen, and then you get to lithium, and then sodium, and then potassium, and rubidium, and larger and larger. And so that last electron, that outermost electron, gets farther away from the nucleus. And so the distance becomes greater and greater. So the nucleus is getting more protons, it is being more positively charged. But if I'm an electron, you got this nucleus over here, and I'm an electron getting further and further away, the effect of me getting further and further away is outweighing the fact that there's more protons in there. Especially if I go from like being an electron in neon to an electron in sodium. Because there's, as I go across a row, it's the same size shell. So I'm just gaining more and more positive charge in the nucleus, and the electron's not getting any further away. But as I jump down to the next row, the electron makes a jump, it skips back. It doesn't just move a little bit, it skips back a good amount. And to further complicate things for the electron, you've got the nucleus over here. It isn't a straight shot between the nucleus and that electron. Every time you open a new shell, all the old shells are still there. If I'm an electron, I don't like other electrons. They're so negative. All these negative charges, I can't handle it. And so between me and that nucleus is essentially shark-infested waters full of other obnoxious electrons that I don't want anything to do with. So I'm not getting a clean view of that nucleus and that positive charge. So I'm even less attracted. And so that's called electron screening. And so the distance grows. I get further and further away. And that distance, that space between me and the protons, those good-looking protons in the nucleus, are just getting filled with other electrons. So for example, if I'm the last electron on sodium, there's 10 electrons between me and the nucleus. If I'm the last electron on potassium, there's 18. Get down to rubidium here, there's 36 other electrons between me and that nucleus. All the way down to francium, where there's 86 other electrons. So not only am I 1, 2, 3, 4, 5, 6, 7 rows back, but all the other rows are completely full. Filled with electrons that I want nothing to do with. And so yeah, there's a nucleus there with 87 protons. It's probably a good looking nucleus. I don't know. I can't see. I have terrible seats. I don't know what's going on there. And so it's a lot easier to take an electron from francium because there's not as much attraction there. None of these put up much of a fight, by the way. These all, we'll talk about why in the next section, but all of these tend to give up electrons, and it's not very difficult, but it is harder to get an electron from lithium than francium because lithium is more electronegative because it has more attraction to that electron. And as I go across, we see a significant jump as well because the nuclei are getting more and more positive. So, what's happening? So we go from the bottom to the top. So we're working our way up. The Drake strategy, start at the bottom, end up at the top, right? Is smaller numbered rows have smaller electron clouds because they have less shells. This equals electrons being closer, and when I say electrons, really what I mean is valence electrons, by the way. Electrons being closer to the nucleus. And in addition, as they get further away, like I mentioned, you get that electron screening. You get the fact that there are other electrons blocking my view of the nucleus. Now that doesn't happen when I go left to right. When I go left to right, it's the same shell. You're getting neighbors, but they're not blocking your view. They're all equally close. But as soon as you drop to the next row, that's like a whole new development on the outskirts of town. You're further from downtown. And so then that fills in, and then boom. Pretty soon, you're way out in the suburbs, and you don't really, whatever's happening in downtown is happening in downtown, whatever. So those are the electronegativity trends. These are going to drive things like, are elements going to share electrons, or are they just going to take them from each other? And that's the difference between a bond and an ion, which we'll talk about more in the next section. So this is a really key idea moving forward, because this underpins all of the behavior of what happens when I put two or more atoms together. What do they do? Because we were just talking about atoms by themselves. And now we're going to start putting them together into compounds, molecules, things like that. And this idea of electronegativity is really what guides that behavior. Between this and the octet rule, so the octet rule combined with electronegativity will really help us understand how these compounds, how matter is going to behave when we treat it this way. Alright, so as always, just let me know if you have any questions. It seems like maybe it's a tricky idea, but just imagine those magnets. They stick together more strongly as they get closer together. They have a stronger pull on each other. And then if you just up the strength of the magnets, they attract more. And then just kind of taking that idea and laying it over the periodic table. The magnets are getting farther apart as we go down here. They are not here. We're turning up the strength of the magnets as we go across. So those are what drive our trends. And, the last thing I would expect you to be able to do with that, I guess it is not like the last thing, but the last thing I'm going to talk about in this video that I expect you to be able to do, that might make a little more sense in English, is to compare different elements. So let's say I want to know what's more electronegative between elements. So let's say we do nitrogen versus oxygen. N versus O. Which is more electronegative? Well, we just look at our trends. Is one above or below the other? No, they're next to each other. Okay. Well, then the one further to the right, which is oxygen, is more electronegative. Because it's further right. That's what the trend says. And I'm not going to do something like, oh, what about phosphorus versus oxygen? There will be no diagonals here. Just left, right, up, down. So we'll do one more. Let's do nitrogen versus phosphorus. N versus P. Oh, move that up there. Nitrogen versus phosphorus. Okay. So, which one is more electronegative? Nitrogen or phosphorus? Well, we're going to look at our trend. And are they next to each other? No. We're looking up, down. So again, it'll just be up, down, or left, right. I'm not gonna do diagonals on you. And the answer is the more electronegative one is going to be higher up, and so it's nitrogen. Because that's what our trend is. As we move up a column, it is more electronegative. And so that's what we're looking for in terms of, being able to compare elements. Just like so, or like so. None of this, none of that, What about molybdenum versus thallium? No, I'm not going to do that to you. It'll be left, right, up, down. So just know your trends, and you can answer that. And we're going to build on this a little bit in the next section, but not too much. Really what's going to happen is this is going to kind of feed into the early discussion, and then there'll kind of be some newer things to recognize that fall out of it. Alright, so yeah, as always, let me know if you have questions. And then we'll be on to the next section.